about dipoles. Hopefully it won't be too new to you, since this is something that, again, would have been covered in your general chemistry class. Polarity, bond polarity, molecular polarity, but we're going to review it this morning. And I'm going to let you know what you need to know for organic chemistry. So molecular polarity and dipoles. We went over valence shell electron pair repulsion theory last lecture, meaning we talked about electron geometry and molecular geometry. And when we understand molecular geometry of a compound, it enables us to determine molecular polarity. But before we get into molecular polarity, we need to talk about bond polarity. And how do we end up having a polar bond? Well, the way that we get polar bonds are when we have differences in electronegativity. That's what it says here. Electronegativity differences result in polar bonds. An example that we looked at last class would be a carbon-oxygen bond, for example. Oxygen has an electronegativity of 3.5. Carbon has an electronegativity of 2.5. They have a difference of around 1. And therefore, there is a difference in electronegativity, which means it is a polar bond. Besides writing those values of electronegativity, we could use the little delta symbols and say delta minus next to the oxygen and delta plus next to the carbon, meaning the oxygen is partially negative, the carbon is partially positive. Another option would be to use a dipole arrow, or a vector, sorry, and to put the arrow pointing towards the more electronegative element and put a cross going through the end on the more electropositive element, or the less electronegative. Anyhow, induction or shifting of electrons within an orbital results in a dipole moment. So how do we calculate a dipole moment? The important thing is that I'm not going to ask you to calculate a dipole moment. However, let's talk about how you would calculate a dipole moment. And this is something you probably did not do in general chemistry. But the way that we calculate a dipole moment, meaning we give a numerical value to it, we quantify it, is to take the amount of partial charge, right, our delta plus or minus, and then we multiply that by the distance by which the partial positive and partial negative charges are separated. And the units that we use to measure dipole moments are debye. And if you're wondering, what is a debye? Well, again, I'm not going to ask you to calculate a debye, but a debye, or 1 debye, is equal to 10 to the negative 18 ESU times centimeters. Now, where does this come from? Well, very simply, if you think about electrostatic units, and this is, again, something that you wouldn't have covered in your general chemistry class, and ESU for ESU is usually somewhere around 10 to the negative 10, okay, so we call that ESU, okay, and again, that's our delta. Whereas the distance between the two nuclei, so we'll put here distance is usually on the order of 10 to the negative 8 centimeters. So if you take 10 to the negative 10 and you multiply by 10 to the negative 8, you get 10 to the negative 18. If you take ESU and multiply that by centimeters, you get ESU times centimeters. And again, that is equal to 1 debye. Now again, you're not going to be asked to calculate any dipole moments on the first quiz or any quizzes, and therefore you don't need to bring a calculator into it or anything like this. We do not need to calculate it. The only thing that you need to know really is that the higher the dipole moment is, the more polar the bond or the molecule is. Let's take a look at some molecules and determine whether they're polar or not, or see how we're able to determine whether they are polar or not. Take a look. It says for molecules that have multiple polar bonds. Yeah, go ahead.
What did you say about when it's higher when it's has a higher dipole, what happens to it?
Yeah, I'm going to get to that in just a second. So basically what I'm talking about is what's on this slide here in table 1.5. And again, we're going to get to this in about 5 minutes or so, that the higher the dipole moment, the more polar the compound, the lower the dipole moment, the less polar the compound.
Okay, thank you.
Yeah, no problem. All right, well, let's go back here and let's take a look at some molecules and see how we can determine whether the molecules are polar or not. The first one that we have here is dichloromethane. So this is called dichloromethane, a very commonly used solvent in organic chemistry. And if we think about the difference in electronegativity between hydrogen and carbon, we saw yesterday that it's less than 0.5 units. Therefore, we don't really consider it to be polar. However, the difference in electronegativity between chlorine and carbon is about 0.5 units, and so we consider this bond to be polar and this bond to be polar. Now, in order to determine the overall polarity of the molecule, what we have to do is we have to sum the individual vectors of all those little dipole moments. And if you've taken physics before, this is something you would have done, which is adding vectors tip to tail. And we get that the resultant dipole is going in this direction right here. You can see that they partially cancel each other out because they almost are going kind of in equal and opposite directions, but not quite. So they cancel each other slightly. However, dichloromethane, when you tally up the vectors, you can see that we do end up with a resultant dipole moment for the entire molecule. Thus, we say that it is a polar molecule. It's not very polar, but it is slightly polar. Now, two molecules that you'd be much more familiar with would be something like ammonia. This is ammonia. And over here we have water. Well, in ammonia and water, we both have polar bonds and lone pairs to consider. When we look at the bonds in ammonia, the nitrogen-hydrogen bonds, well, we see that nitrogen is much more polar than hydrogen. There's a difference of electronegativity of about 0.9 units here. And that's why we have all these vectors pointing towards the nitrogen, because the nitrogen is more electronegative. We would put the delta minus and a delta plus here on each of these if you want. However, in this picture or this diagram, we're using vectors. We can also put a vector where the lone pair is. Since a lone pair is simply a pair of electrons, but it's not shared, you can imagine that there's more negative electron density here by the lone pair than there is by the nitrogen. And so we have also a dipole going in the direction of the lone pair, and that would count for any lone pair. If you tally up all four of these vectors, 1, 2, 3, 4, you can see that the net direction that they are pointing is going straight up. We have a tripod, so to speak, for these ones here. They're all pointing up and at equal and opposite angles, having bond angles of around 120 degrees, of around 107 degrees. However, we also have the dipole on the lone pair, and so that is why ammonia is a polar molecule. If we go over to water, you see that we have two polar bonds and we have two lone pairs. Now, since the molecular geometry of water is bent, its electron geometry is tetrahedral, we have a net dipole moment here. You can see that we have two polar bonds going between the oxygen and the hydrogen, and then we also have two dipoles going to the two lone pairs. When you tally up all four of those dipoles, you see that we get a resultant dipole moment going in this direction, and that is why water is a polar molecule. Again, in order to determine whether a molecule is polar or not, we have to understand molecular geometry. If you're unable to elucidate the correct molecular geometry for a molecule, you'll oftentimes get an incorrect answer for the overall molecular polarity. Let me give you an example of that, okay? What would water have, or would water have a different dipole moment if it were linear instead of bent? Again, in this model here, you can see that it's bent. This bond angle is less than 109.5 degrees. It's around 104 degrees. But if water was linear, and I'm just going to scribble it, I don't know, I'll just scribble it up here. If water was linear, and it's not, but if it was, it would look something like this. You'd have a dipole going in this direction, a dipole going in this direction. Those would cancel each other. You'd also have a dipole going towards this lone pair and one going towards this lone pair. And all dipoles would cancel, and it would look like it would be a non-polar molecule. But we know that water is a very polar molecule. And so, again, there's nothing wrong with writing the Lewis structure of water like this. However, it doesn't represent its molecular geometry, and hence you would not be able to tell that the molecule is polar unless you were able to give it the full treatment and understand that it has a bent molecular geometry, a tetrahedral electron geometry, and therefore it is a polar molecule. You know, this slide just summarizes a lot of what I said already. You can see here, it says you have to know the molecule's molecular geometry before you can even analyze polarity. This is why chemistry is an additive subject. How are you able to draw the molecular geometry of a compound? Well, think about it. First, you have to know electron configuration. Then you have to know the Lewis structure of an atom. Then you've got to be able to draw the Lewis structure of the molecule correctly. Then you have to be able to apply VSEPR, valence shell electron pair repulsion theory, in order to determine the electron geometry. And finally, the molecular geometry. Then you have to understand bond polarity. Then once you put in the vectors in the proper orientations with that molecular geometry, you're able to determine whether the molecule is polar or not. Again, put it another way. If you do not draw the molecule with proper geometry, you will not be able to assess the polarity. Okay, you're going to end up making a mistake on that. So make sure you're fully aware of all the molecular geometries that we covered in last class. Here is a quick summary of all of them. You need to know that when we have electron geometries that are tetrahedral, but you have two lone pairs, that you end up with a bent molecular geometry, like in water, we just looked at. But when you have one lone pair, you end up with something that's trigonal pyramidal, and so on and so forth. So make sure you're fully aware of all of these different molecular geometries. And again, it's a lower number of molecular geometries than you would have seen in General Chemistry 1, because in that class, you would have learned the seesaw and the T-shape and the trigonal bipyramidal and the octahedron and the square pyramidal and the square planar. And we don't cover any of those molecular geometries in this class. Sometimes when we want to represent a polar molecule and show where its regions of high and low electron density are, we use what's called an electrostatic potential map. So an EPM, an electrostatic potential map. And these are a great way to give us a visual depiction of polarity. In our textbook, whenever he uses a red color, like you see in this electrostatic potential map right here, you can see that that has a greater density of electrons. So you could say it's more negative, or you could say, you could say greater electron density. And when it's blue, it means it's more positive, or you could say lower electron density, like that. Okay. Again, there's nothing wrong with using the delta symbols like this, partial negative, partial positive. There's nothing wrong with using a dipole arrow, but sometimes a picture is worth 1,000 words, and we use electrostatic potential maps, which are generated on calculators. All right, somebody asked me in the chat, are nonpolar or polar bonds harder to break? That really depends. It doesn't have anything to do with whether the bond is polar or not. It has to do with the overlapping of orbitals. And so the more efficient orbital overlap is, the stronger a bond is going to be. The weaker it is, the less orbital overlap there is, the weaker there's going to be. There's no direct correlation between bond polarity and bond strength. Okay, so electrostatic potential maps. And the question that came up just a few moments ago was, okay, I get it. You're not going to ask me to do a calculation. In fact, I even have it on the slides here, so you can take this and show it, stick it in my face if I ask you a calculation. It says no calculations will be required on the first quiz. However, you have to understand the concept and definition of a bond dipole moment. The dipole moment, mu, is equal to the partial charge multiplied by distance. So the greater the partial charge, the greater the dipole moment. So if we look at these values of dipole moments for some common solvents here at 20 degrees Celsius, all you need to know is that the higher the number, the more polar the compound is. If we compare acetone with ethanol, let's say, well, you can see that acetone has a dipole moment of 2.69 dBi, whereas ethanol has a dipole moment of 1.66 dBi. Therefore, we can conclude that ethanol is less polar than acetone. If you're wondering, can something have no dipole moment at all? The answer is absolutely. Right? If we have a compound that has no polar bonds in it, or if all the dipoles cancel, we can end up with molecules that have no dipole moment, so 0 dBi. Take a look at carbon tetrachloride. There are polar bonds in carbon tetrachloride. I can even show it to you if we just look at the Lewis structure of carbon tetrachloride. And I'm not going to put in all the lone pairs on the chlorines in the interest of time, but we have a polar bond in this direction. We have one in this direction. We have one in this direction and in this direction. However, all four of those dipoles cancel. And since they cancel, we end up with no dipole moment. With pentane, it's different but similar. Okay, we have no dipole moment. However, the reasoning is different. The reason is because we have no polar bonds in the molecule. No polar bonds in the molecule, and therefore we cannot have a dipole moment. You don't have to memorize these values of, the dipole moments. However, you need to understand that the higher the dipole moment, the more polar the compound. Again, there will be no calculations on the quiz. No calculations. All right, this is question 1.28 from the textbook. And it says, identify whether each of the following compounds exhibits a molecular dipole moment. For compounds that do, indicate the direction of the net molecular dipole moment. The first one, CH3OCH3, this is called a partially condensed structure. It tells you the order in which the atoms are bound together in the molecule. And we went over Lewis structures yesterday, so I'm not going to take a lot of time in drawing the Lewis structure. However, if we draw the Lewis structure, we have carbon and then an oxygen with two lone pairs, and then another carbon, and then we attach 3 hydrogens to each carbon, and there we go. The problem with this, and there's nothing wrong with this Lewis structure, I mean, it's perfectly fine. However, it doesn't enable us to determine the molecular geometry, or it doesn't show us the molecular geometry, and hence it would be difficult to determine whether the molecule has a dipole or not. First thing I'm going to address is the carbon-hydrogen bonds. Those are completely non-polar bonds. So we don't even have to worry about those affecting the dipole of the molecule at all. But my question to you this morning is, are there any polar bonds in this molecule? If so, could you identify where they are? Are there any polar bonds in this molecule? Could anybody identify a polar bond? Can you guys hear me? Yeah, absolutely. Between the oxygen and the carbon, there's a polar bond. Absolutely. Thanks, everybody. Good. So we have a polar bond here and a polar bond here. The next thing I want to ask you is that if we look at the bond between the carbon, the oxygen, and the oxygen has 2 sigma bonds and 2 lone pairs. What would the molecular geometry around the oxygen be? Could anybody tell me that? What would the molecular geometry or the bond angle be? Yeah, it would be bent. Thanks, Clinton. Absolutely. If you're unsure where Clinton got that answer from, let's just take a look back in our slides. We scooch back to section 1.10 to that table that we looked at again this morning. If you have a steric number of 4, that means the hybridization of the oxygen is sp3, and the oxygen has 2 lone pairs on it. That means that its molecular geometry is bent. And so if we go back here, now we're going to redraw the molecule. We're going to redraw it with a bent molecular geometry. So we're going to have our oxygen. We're going to have 1 bond going down here to a CH3. I'm just going to condense that since there's no polar bonds in there. And then we have the other CH3 down here. And then we have a lone pair and a lone pair. Now we can tally up the dipoles. And you can see that we have a polar bond going this way because oxygen is more electronegative than carbon. We have another polar bond going this way. We could even put the lone pairs in orbitals, or we could draw them kind of like in little lobes here. So in these sp3 hybridized orbitals. So we could put a lone pair in here and a lone pair in here, like that. And when we tally up all those dipoles, so if we have this one and this one, what's going to happen is we're going to end up with a resultant dipole going in this direction. And so this compound is a polar compound because the dipoles do not cancel out. They tally up to give you this resultant vector. Now, something else that I didn't really show here completely is, however, this molecule has a tetrahedral electron geometry. So if you want to draw it even more accurately, you could leave the two lobes or the two orbitals with the lone pairs in the plane. And then you could draw one of the bonds to a methyl group or CH3 group going out and the other one going back like this, because that helps you represent the tetrahedral electron geometry. So we have a polar molecule. All right. I'm going to show you the next one kind of quickly. It's CCl2Br2. It's kind of an interesting molecule because you've got carbon that has an electronegativity of 2.5, chlorine is 3.0, and bromine is not much less than chlorine, but it's 2.8. And so if we draw the correct molecular geometry here, we have the two chlorines. I'll draw those in the plane. We have a bromine in the back, and then we have a bromine out front like this. This is just a Lewis structure. I'm going to put in all my lone pairs this time like that. Do we have any polar bonds in this molecule? Could anybody tell me? Could anybody describe where I would put a vector in here or tell me which bond? Yeah, the carbon-chlorine bond is polar. Right, the difference is 0.5, which falls in the range of polar. And so we have a dipole going towards the chlorine. We have a dipole going towards this chlorine. We also have a slight dipole. It's not big. It's practically nonpolar between the bromine and the chlorine, but it's so small. We'll just put a tiny little arrow here and a tiny little arrow here that it doesn't really affect the overall dipole. And so the resultant dipole, if you tally up these two vectors, is going to be in this direction. Again, it's not going to be a huge dipole, but this is going to be a polar molecule because you do have a resultant dipole or an overall dipole for the entire molecule. And for the last one, this would be called trans 1,2-dichloroethylene or ethene. Could anybody tell me? I'll just zoom in here on J. You think this would be polar or nonpolar? Anybody? Polar or nonpolar for this guy? We know there's polar bonds. Yeah, we know there's polar bonds because we just identified the carbon-chlorine bonds as being polar. We said, yeah, they're totally polar. And thus, if we draw a dipole in this direction, sure, they're polar. But what happens to these two dipoles? What do they do to each other? Absolutely, absolutely. I'll give you a clue. Starts with C, ends with ancel. That's right. They cancel. So we'll just write here dipoles. Dipoles cancel. Therefore, non-polar. Not a polar molecule because the dipoles cancel one another out. And there you go. That's a little bit of identifying polar molecules. And that's something that we need to be able to do as organic chemists. Again, something that you would have covered. This is a review of General Chemistry 1. That's where you would have seen this, not General Chemistry 2. But very important that you understand molecular geometries and bond polarity, and then that you're able to determine whether a molecule is polar, yes or no. Cool. Let's move on. We're getting closer to the end of chapter 1. It's a very long. So somebody asked me if the dipoles are on opposite sides, do they cancel? Not necessarily. Not necessarily. Just because they're on opposite sides doesn't mean they cancel. I mean, if you look at this compound here, you have a dipole over here and a dipole here. They're on opposite sides, but they don't cancel each other out. If they're pointing towards each other directly or in equal and opposite directions, then they can cancel each other out. How do you know to put the chlorine on the same side in CCl2Br2? Well, that's just a regular old, three-dimensional drawing. I mean, I could have drawn that compound any number of ways. As long as I showed that the carbon is tetrahedral, you have to know how to draw a tetrahedron. So if you have the bond angles like this, I mean, you could put the chlorine here, you can put a chlorine here, you can put a bromine here, a bromine here. I mean, these are still the same molecule. Okay, they just have to be, it just has to be a tetrahedral drawing of the molecule. I just find that it's easier to show it this way to get the point across to my students. Does that answer the question? The great thing about organic chemistry and science in general is if it's right, it's right. There's not a whole lot of my opinions or anything. Okay, cool. All right. If you raise your hand, I'm not sure if that's a question or not, but I'm unable to really see who's doing that. So if you raise your hand, I think the best thing to do would be either to unmute your mic and ask me a question directly, or you can type it in the chat. Either one will work. And if neither of those things, go ahead.
I have a question about like the second way you drew the CCl2Br2. Wouldn't it be non-polar because like they're kind of in opposite directions, the dipoles? I was just confused about that.
They're kind of, in a way, they're in opposite directions. But remember that these two representations are the exact same molecule. I didn't change anything. All I did was rotate the molecule slightly is all. Right?
Okay.
So if you look at this dipole is going toward this way, and this one is going this way, but it's going backwards like that, those still will tally up to give you a dipole going in this kind of direction. And so that's this dipole that I drew, but it's just tilted a different way.
Okay.
All right. Now, manipulating objects, three-dimensional objects in your mind's eye is not an easy thing to do. Go ahead.
I'm still just confused as to like if they're both pointing in opposite directions in CCl2Br2, then why wouldn't they cancel out like in C2Cl2H2?
Because they're not pointing in opposite directions, right? These bond angles are all 109.5 degrees. So that's not 180 degrees. If they were going in opposite directions like this, they would cancel each other out. So you can see how these are going in direct opposite directions. Okay, that's like a tug of war. They're both pulling in equal and opposite directions, but in here, in this molecule, they are not.
Okay, I understand now. Thank you.
Yeah, no problem. All right, and this is where molecular model kit might come in handy. So model kit, we'll put model kit question mark. You can buy a model kit, like I said, from Amazon for, I don't know, my students buy them for $25, and they definitely can do anything you would need them to do in this class. But what's great about building a model is that you're able to hold it in your hand and move it around, and you don't have to think about manipulating the molecule in your mind. You know, I have students, I have a student who wrote the DAT recently, which is the entrance exam to dental school. And he was showing me how some of the questions that they would ask is they'd give some kind of shape, and they'd say rotate clockwise 180 degrees, flip backwards, you know, or flip towards the viewer 120 degrees, and then rotate to the left 109.5 degrees. And then you have to be able to tell, okay, well, which one of these potential answers is the actual, you know, orientation that I would have now, right? And the reason why it's important for somebody who's a dentist to be able to do that is if you think about it, when they, you know, are working on your molars, they're not standing on the back of your tongue. They don't have that capability yet. And so what they're doing is they're using mirrors, right? They're looking backwards. And so they have to know that the person has the aptitude to be able to look kind of backwards and imagine things like that. And that's a skill that can be learned for sure. Anyhow, let's move on from there and let's talk about intermolecular forces, IMFs. So IMFs. If I don't get to your question on the chat or something, just shoot it to me in an email and I'll do my best to get back to you. So it says many properties like solubility, boiling points, melting points, densities, etc., are affected by the attractions between separate molecules. All right, let's say we have two water molecules. If I draw a water molecule here, and then I put another water molecule, I don't know, over here somewhere like that. The forces that hold the water molecules together, meaning the bonds, those are what we call intramolecular forces. So we'll say here intramolecular forces or bonds, right? You think about if you're traveling intranationally, it would mean you're traveling inside a country. Okay, so intramolecular forces are the forces that hold the molecule together. So any bond would be an intramolecular force. But if you have a glass of water, let's say we just have a glass, you know, and we have some water in that glass. Well, why doesn't the water all just spontaneously vaporize into a gas or be converted into steam, you know, in just a matter of seconds? The reason why is there must be something holding those water molecules together in the liquid phase. And that force that holds water molecules together, or the force of attraction between different molecules, is called an intermolecular force. So this is what we call an IMF. And if you're thinking, well, the force that's holding water molecules together is hydrogen bonding, which it is, you'd be absolutely right, okay? And so the three intermolecular forces that you need to be aware of in this class, and there are others, but the ones that are going to come up in organic chemistry are dipole-dipole forces or dipole-dipole interactions, hydrogen bonding, and the last one would be the London force or the fleeting dipole or the instantaneous dipole, which we sometimes call dispersion forces. So these are the ones you need to know. Out of all these, the strongest is the hydrogen bond, so strongest. And then dispersion forces are the weakest, and dipole-dipole forces are somewhere in the middle. Somewhere in the middle. So let's start with the middle. Okay, let's start with the ones that's intermediate, and we're going to take a look at dipole-dipole forces. Where do they come from? Well, they come from, or they are a result of a molecule having a permanent dipole in it. Check this out. These are nothing more than electrostatic potential maps of 3 molecules of acetone. So I'll draw another one over here. So this is acetone or nail polish remover. It has many uses, but this is acetone, okay? And in acetone, there is one polar bond. We can represent that dipole using a vector like this, or we can use the delta symbols, and we know that oxygen is more electronegative than a carbon, so we put delta minus here and delta plus here. Now, if I have a sample of acetone, if I just have a bottle of acetone, and acetone is a liquid at room temperature, the molecules are free to tumble around in the bottle and just, you know, freely. However, what is going to happen, or what is very likely to happen, is that since you have a delta minus on one molecule of acetone, it's going to be attracted to the delta plus on the carbon of another molecule of acetone. And that causes them to kind of line up the way that you have here. And so a dipole-dipole interaction, and in fact, any type of intermolecular force, is nothing more than an electrostatic attraction. What's electrostatic attraction? It's the attraction between a positive and a negative charge. We're not talking about cations and anions. We're talking about a partial negative and a partial positive, but there is a force of attraction between those two partial charges. It's not as strong as a bond, but it's strong enough that it has an effect on the molecule or molecules, and it has an effect on their melting points or boiling points. You can imagine that if boiling is the act of taking something that's in the liquid phase and converting it into a less associated gaseous phase, that the stronger the intermolecular forces are between two molecules, the higher the boiling point will be. And that is absolutely true. So the dipole-dipole interactions between acetone molecules increases its boiling and melting points. But if you have a molecule that even looks quite a bit like acetone, but it has no dipole in it, it's going to have a lower melting and boiling point. Let me give you an example of that. If you compare this molecule, which is isobutylene, to acetone, it looks a lot like acetone, doesn't it? It has 2 CH3 groups on a carbon. You have a double bond, but instead of an oxygen, here you have a CH2. We call a CH2 a methylene in organic chemistry. If you compare the melting point of isobutylene to acetone, you see that its melting point is much lower. It's negative 140, whereas acetone's is negative 95. You see that the boiling point of acetone is much, much higher. It boils at around 56 degrees, whereas isobutylene is a gas, even when, 0 degrees Celsius, it's even a gas then. Why is that? It's because of this right here. Acetone has a dipole in it. So it has that partial negative and partial positive that can produce the dipole-dipole forces, and therefore it has there's a stronger force of attraction between two acetone molecules, whereas in isobutylene there are no polar bonds. There's no polar bonds in there, so there would be no dipole-dipole force, and there's definitely no hydrogen bonding in here. And so that explains why acetone is a more polar molecule and why it has a higher melting and boiling point than isobutylene. Give me a thumbs up if you follow me on that concept of the whole acetone having a dipole. Great results in a change in the melting point and boiling point, being that they are both higher than that of isobutylene. Great. Well, if you understood that, then you're definitely going to understand hydrogen bonding, because hydrogen bonding, if you've ever wondered about it, let's say you didn't quite understand it in general chemistry, hydrogen bonding is nothing more than a dipole-dipole force, except it's really strong. That's all there is to it. It's nothing more than that. Hydrogen bonds are really strong intermolecular forces because the partial negative and partial positive now they're really big. Okay, they're really big, they're really strong. And so hydrogen bonding is not a bond. And if you're like, oh shoot, why do you call it a bond then? Well, first of all, I didn't create it. I didn't invent the name, so don't throw anything at me. But hydrogen bonding is nothing more than an electrostatic force. And in fact, it's much weaker than a covalent bond, much, much weaker. It's about 20 times weaker than a covalent bond. And something that you need to be able to do as an organic chemistry student is identify whether a molecule will possess hydrogen bonding or if it will not possess hydrogen bonding. How do you do that? You look for a bond between hydrogen and one of three elements: oxygen, nitrogen, or fluorine. If you have a hydrogen bound to any of these elements in your compound, you can have hydrogen bonding. The way that people remember these sometimes is they'll say fluorine, oxygen, nitrogen. You've got to look for fun. Fun? You got to look for fun. Okay, if you find fun, either one of those bound to hydrogen, then you can have a hydrogen bond. If we look at the two examples found at the bottom of this slide, you see we have water and ammonia. We'll start with the water. Well, we know that water, even though it's a really small molecule, water has a molar mass of 18.02 grams per mole. It's not very big, but it's got a really high boiling point of 100 degrees Celsius, even though it's this tiny little molecule. Why is that? It's because of hydrogen bonding. How do we represent that? Well, we know that there is a dipole between the oxygen and the hydrogen. The difference in electronegativity is going to be 3.5 for the oxygen, subtract 2.1 for the hydrogen. That gives you 1.4. But the oxygen is more electronegative, so we can put a delta negative here. You can see that somebody did it over here. And what we do is we draw a dashed line between the partial positive, or delta plus, on the hydrogen and the delta negative on one of the lone pairs. So you could even draw in another water molecule if you wanted, just for fun. No pun intended. We could do something like this, and then you could say, well, this is delta negative, this is delta positive, and so we would draw a dashed line between the two like that, and there you go. That represents a hydrogen bond. Another thing that makes water so unique is that water is the only compound that can completely maximize its hydrogen bonding because it has two lone pairs and two hydrogen atoms. And so every lone pair and every hydrogen atom can be occupied in a hydrogen bond in water. Whereas if we look at something like ammonia, we see the hydrogen bond here between the lone pair on the nitrogen and the hydrogen, which has a delta plus. But here we have one lone pair and three hydrogens. And so we cannot offer a hydrogen bonding opportunity to every hydrogen atom in a molecule of ammonia. And that's why ammonia doesn't have a high boiling point compared to that of water. Hydrogen bonding, very, very important intermolecular force. Why? Because it comes up in things like biochemistry. And check this out. Only when a hydrogen shares electrons with a highly electronegative atom, like oxygen, nitrogen, or fluorine, it's going to carry a large enough partial positive charge to have a hydrogen bond. If you take a look at these two molecules here, we have an OH bond and an OH bond, and therefore we can have a hydrogen bond between the delta plus on the hydrogen and the lone pair on the oxygen. Even though you have large partial positive charges when we're looking at hydrogen bonding, a hydrogen bond is still about 20 times weaker than a covalent bond. So it's nowhere in the neighborhood in terms of strength compared to a covalent bond, but it is a lot stronger than a dipole and stronger than a London force that we'll look at next. Another thing you need to know about solvents and about hydrogen bonding is that some solvents that we use in organic chemistry can participate in hydrogen bonding. And when they can, we call those protic solvents. So any solvent that can participate in hydrogen bonding is called a protic solvent. An example would be something like acetic acid. Why is this a protic solvent? Because it has an OH bond in it, and therefore it can participate in hydrogen bonding. Other examples would be things like water, of course. Water obviously can participate in hydrogen bonding. And ethanol, which is this compound, can participate in hydrogen bonding, so ethanol. And we will see others along the way. If I show you any kind of solvent in organic chemistry, but it doesn't have an OH bond or an HN bond or an HF bond in it, it cannot participate in hydrogen bonding, and then it is called an aprotic solvent. So no hydrogen bonding means it's aprotic. I have two examples here, diethyl ether and dimethyl sulfoxide. These are both widely used solvents in organic chemistry. However, neither of them can participate in hydrogen bonding. And you might be looking at this one, diethyl ether, and saying, well, come on, there's an oxygen here, and there's an oxygen here in DMSO, dimethyl sulfoxide. Can't those participate in hydrogen bonding? And the answer is no. They're not going to hydrogen bond to one another because there's no hydrogen bound to this oxygen, and there's no hydrogen bound to this oxygen. And if we have oxygen, we have to have a hydrogen bound directly to it, like we do here, in order for hydrogen bonding to occur. Other examples of aprotic solvents would be things like dichloromethane that we looked at earlier this morning. So dichloromethane would be aprotic, and hexane, which is this, CH3, CH2, 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 CH2. No, I get an extra CH2 in there, CH3. This is called hexane. This is also aprotic, okay? So there we go. We're going to see a variety of protic and aprotic solvents. And I'm not going to ask you to memorize a bunch of solvents in the first week of class. However, you will have to be able to recognize when a solvent is protic, when it can participate in hydrogen bonding, and when it's aprotic because it cannot participate in hydrogen bonding. Well, let's take a look at three compounds that are all isomers of one another. Each one of these compounds has the same molecular formula, C3H9N. Every single one of the compounds on here, trimethylamine, ethylmethylamine, and propylamine, all are C3H9N. All are C3H9N. And so based on what we learned in our first class, these would be all constitutional isomers of each other. But you can see that they all have different physical properties. They all have different boiling points. Could anybody tell me why trimethylamine has a much lower boiling point than ethylmethylamine and propylamine? And I'm not looking for a complex answer. Why does this one have a boiling point that's so much lower? Trimethylamine, much lower boiling point. But the other two have boiling points of 37 and 49 degrees respectively.
It doesn't have any hydrogen bonds.
Exactly. That's it. Nothing more than that. It is incapable of hydrogen bonding. So no NH bonds, therefore no hydrogen bonding. Absolutely. Whereas if you look at these two, we have potential for a hydrogen bond. And here we have two possibilities for hydrogen bonding. So NH bonds, therefore hydrogen bonding. And we know that hydrogen bonding is the strongest of the intermolecular forces, and that explains why these two molecules have higher boiling points. You see that propylamine has the highest boiling point. Highest boiling point. Why? Because it has the most NH bonds, and therefore it can do more extensive hydrogen bonding. There's more opportunities for hydrogen bonding, if you will. You know, hydrogen bonding is a really important concept for my students to understand. Why? Because it comes up in biology, biochemistry, cell biology, molecular biology. And hydrogen bonds are the forces that cause DNA to form the double helix and for proteins to form into an alpha helix. This is the alpha helix shown of a protein. So a protein is nothing more than a polymer of amino acids. And here we have the double helix that's found in DNA. If you look at these dashed bonds, either in the DNA, in the alpha helix here or in the DNA, what holds both of these helices, or the helix and the double helix together, are hydrogen bonds. Even if you've ever seen a beta pleated sheet before, so a protein secondary structure can be either an alpha helix or a beta pleated sheet. And if you've studied biochemistry, you might have seen this before. That's also held together with hydrogen bonds. Okay, so very important that we understand hydrogen bonding in order to further our knowledge in chemistry, and especially for those who are interested in moving on into biochemistry. Well, that brings us to the last type of intermolecular force that we're concerned with in Chemistry 3101, and that is the weakest of all the forces, and that is London dispersion forces. Sometimes we call these fleeting dipoles. Okay, so we call this a fleeting dipole. Sometimes we call it a transient dipole moment. Sometimes we call it an induced dipole. They all mean the exact same thing. If you're wondering, what is this? Well, if you have two molecules that are nonpolar, they are still going to have some kind of attractive force between them. Let me give you an example. The simplest example I can think of off the top of my head this morning is if we have bromine, Br2. So this is the Lewis structure of bromine, and bromine is actually a liquid at room temperature. Now, there's no dipole in Br2 because both atoms have the exact same electronegativities, 2.8. Therefore, the delta En is 0. Could write that in here, delta En equals 0, but it's a liquid. Why isn't bromine a gas? Well, there must be some reason why, and the reason why is that even though we have a nonpolar molecule, there can still be a small force of attraction that we call a London force. Let me explain what a London force is. Check this out. A nonpolar molecule normally will have all of its electrons spread out evenly around the nucleus so that all the charge is balanced out. We know the nucleus is positively charged. We know that electrons are negatively charged. But if they're all evenly dispersed around the nucleus, or the nuclei, then the molecule, all the partial positives and partial negatives, or all the negatives and positives, I should say, they're all going to cancel each other out. And so we get something that is completely nonpolar. However, electrons are like hyperactive children. What do I mean by that? It means that if they can move, they will. Put another way, electrons are in constant random motion. Electrons love to move within the molecular orbitals of a molecule. So what if in a moment of time, just based on probability, if all the electrons are moving very quickly, what would happen if all the electrons just kind of bunched up on one side of a nonpolar molecule? And this is what's being shown here. This is a nonpolar molecule. This is called pentane, which is neither here nor there at the moment. However, if all the electrons gang up on one side just for a split second, well, what's that going to do? It's going to cause any electrons that were over here to be repelled. They're going to move to this side of the molecule, and therefore that's going to render this side delta positive. And then I'm going to have a force of attraction between all these delta positives and delta negatives. Now, that doesn't last long. It is temporary. Why? Because those electrons, again, are like hyperactive children. They make that dipole very quickly, and then they move, okay? But if you have enough molecules, moles of them, eventually you tally up enough of those weak interactions, and it tallies up to, or ends up being something that is meaningful, even though it is relatively weak. So the result is that fleeting attraction between the two molecules. Again, fleeting means rapid, short, quick, doesn't last long. And so we end up with an intermolecular force that is very weak. And like I just said, if there's enough of them, they can add up to be significant. The London dispersion forces, the fleeting dipole. You know, if you've ever wondered, how does a gecko, and why is it able to climb up a wall? And I don't own a gecko or anything like that. Well, it doesn't actually use suction cups on its feet, or it doesn't use any kind of chemical reaction to hold itself on a wall. It actually has very tiny fibers, so to speak, called, I think they're called setae or something, on the ends of the gecko's feet, which means it has all these little hairs on the bottoms of its feet. And what it does is that even though when the hairs touch the wall, there's a very weak London force between the hair and the wall, if you add up enough of those hairs, and there are millions or 500,000 hairs on each one of the gecko's feet, I think, it makes enough London forces that enable it to stick on a wall. And if you've ever studied biomimicry before, which is, you know, where science try to mimic things that they see in nature, they're trying to develop all kinds of ways to enable humans to climb up walls. I'm not really interested in climbing up a wall, but if you're interested in that kind of thing, you're like, I'm climbing the wall already, Mr. Dion. I'm enrolled in organic chemistry in the summer. Well, if you're interested in it, that might be something that would be more interesting for you to read about. And there's a little blurb about that in our textbook. Now check this out. London dispersion forces are the reason why molecules with more mass, generally speaking, have higher boiling points. You can see that as we go from butane to pentane to hexane, we have a higher and higher boiling point. It goes from 0 to 36 to 69. Why is that? It's because as the molecules get longer, there's more interaction between the two molecules because there's more surface area for the molecules to share with one another, and therefore you can have more fleeting dipoles, and therefore you have a higher boiling point, right? So there we go. So the longer the molecule, the more intermolecular forces there's going to be. Let me just go to a camera here for a second, just to make sure everybody's with me. I'm just going to stop that. We're still recording, but let me talk with my hands for a second. Can everybody see me? I'm assuming you can. Okay, so here's how I think of a London force. Now, this is going to be kind of a funny demonstration, but let's imagine I gave you a piece of Velcro that was 2 inches long. Okay, 2 inches long. And if you've ever looked at Velcro before, you'll notice that one side of the Velcro will have kind of like little hooks on it like this, and the other one's kind of fuzzy, and the hooks hook into the fuzz. Anyhow, that's neither here nor there. But if I gave you a piece of Velcro that was 2 inches long, and I said, Zoe, I want you to tear this apart. And you'd say, okay, there we go. Did it, Mr. Dion. Did that take up some of your body's energy? Did you use up some ATP to pull that apart? The answer is yeah. Not a lot, but you did. Now, let's say I said to Angel, I said, you know, I'm going to give you a piece of Velcro, but it's going to be 10 meters long. And it's the same force holding the Velcro apart, but you've got to go shh, 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 shh. So when you tear that apart, are you using more energy? The answer is yes. It's still the same force holding the Velcro apart, but since there's more surface area in contact between the two pieces because they're longer, it takes more energy to break them apart. And that's why it takes more energy to boil or to vaporize a compound that is longer than a compound that is shorter. Give me a thumbs up if you follow me on that idea. The old Velcro analogy. Like, yes, Mr. Dion, my favorite pair of Velcro shoes. I was looking at those and thinking about intermolecular forces. Anyhow, I hope not. But anyhow, let's go back here. So let's get back to the slides. Okay, so let's go back here and check this out. I think you'll find this really interesting. Now, what happens if you have molecules that have the same molecular formula? So these are all C5H12. These are all constitutional isomers, pentane, 2-methylbutane, and 2,2-dimethylpropane. But check it out. They all have very different boiling points, 36, 28, 10. Why is that? It's because as you have more branching, you know, here we have a branch, here we have 1, 2, 3 branches sticking off, or however you want to look at it. Maybe you could just say it's kind of like 2 branches. I think is probably the easier way. But anyhow, and here we just have, you know, 1 chain. Here you have a chain with a branch. Here you have a chain with 2 branches. The more branching that you have, the lesser ability that the molecules have to pack with one another or interact with one another. And so the London dispersion forces are still there, but since there's less ability for the molecules to interact with each other, they have lower and lower boiling points as you have more branching. Well, that's a lot of me rambling on. And with all that in mind, let's try a question. This is question 1.30 from your textbook. It says, for each of the following pairs of compounds, identify the higher boiling compound and justify your choice. So let's take a look. The first one is A. And if I call this compound A and I call this compound B, they both have the same molecular formula. They're both C6H14O. Okay, they both have the same molecular formula. But can anyone tell me which one would have a higher boiling point? Would it be A or B? And again, there's no trick questions. Yeah, absolutely. Thanks, Nicole. Thanks, Andrew. Angel. Perfect. Koi. Absolutely. Yes, the answer is B. So we'll put here higher boiling point because less branching, right? It's got more of a linear shape, and so less branching. If we go to the next one, we go to B, I'll call this one C and I'll call this one D. Which one would have a higher boiling point, the C or the D? Yes, absolutely. Now this one's trickier because they don't have the same molecular formula. Could anybody tell me why D has the higher boiling point? You're all right. Everybody's correct. Why would that be? Why would it take more energy, higher molar mass? Absolutely. So we'll put here higher because higher, excuse me, molar mass. The next one is a dandy. I'll call this one E and I'll call this one F or C. Anybody have an idea? Would it be E or F? Hopefully you get this one pretty quickly. They both have the same molecular formula. Oops. Where were we? Yeah, so I think I called this one E and I called this one F. Anybody? I don't see an answer. Did you guys lose me? Could anybody tell me which one of these would have a higher boiling point, E or F?
There's a bunch of us that are saying F.
Oh, okay. I can't see it in the chat. It must have froze or something. All right, cool. Thanks. And I think that everybody probably knows the reason why. It's because F possesses hydrogen bonding. So hydrogen bonding, we'll just scribble that in there. And then the last one, you can see that both of these molecules are capable of hydrogen bonding. However, the one on the left-hand side is going to have a higher boiling point. We'll put higher because linear, or put another way, less branching, just like that. There we go. Nothing to it. Okay, that brings us to the very last section of the chapter. Let me try closing the chat and then I'll reopen it for myself. Oh yeah, I can see it now. I don't know, something was wrong there. All right, so let's go back here. Section 1.13 is the last section of the first chapter, which is a really long chapter, very long chapter, chapter 1, and it is solubility. The number one thing you need to know about solubility is this axiom, like dissolves like, which means if you have a polar compound, it's going to dissolve in a polar solvent. If you have a non-polar compound, it's going to dissolve in a non-polar solvent. And this goes right back to that whole idea of polarity. All right, you need to understand polarity. Put another way, it says here that polar compounds generally mix well with other compounds that are polar. If the compounds mixing are all capable of hydrogen bonding, well, they can form a strong dipole-dipole or strong hydrogen bonds between one another, and there's no reason why they shouldn't mix. However, if we have a nonpolar compound, nonpolar compounds really mix well in nonpolar compounds, right? If we think about oil and water, why don't oil and water mix very well? They don't mix at all, really, because oil is nonpolar and water is polar. Therefore, they don't mix. Whereas if you take something like acetone, which is nail polish, it dissolves in water no problem. Why? Because acetone is polar and water is polar. And that is the main rule that you need to know about solubility. Like dissolves like. It's difficult to get a polar compound like water to dissolve or to solubilize a nonpolar compound like oil. And so you might wonder, well, how do I wash my hands? You know, if you want to clean your hands, which have oils and grease on them, you know, we go and wash our hands and we use water. However, you can't just use water to wash oil and grease off your hands. What do you need? You need to have soap. Well, how does soap work? How does soap enable the water? How do they work together to dissolve oil and grease on your hands and remove them and send it down the drain? Well, what happens is that soap is a very interesting molecule. And this is a molecule of soap down here. So this is just a soap molecule. And you can see that soap has two parts to the molecule. It's got a hydrophilic portion. Hydrophilic means water loving, and that is polar. This is what we call a carboxylate in the green box. And then it's also got this huge tail at the end here, which is just nothing but a bunch of non-polar carbon-carbon and carbon-hydrogen bonds. So you've got the two parts of the soap molecule. You've got a polar portion and a non-polar portion. Well, what's cool about that is that the non-polar part can interact. I'll use my blue highlighter. The non-polar portion can interact and dissolve dirt. Dirt can interact, and oil and grease can interact with the non-polar portion, whereas the polar portion will interact with water because water is polar and dirt is non-polar. Well, what happens when soap molecules get in water is they spontaneously organize themselves to form what's called a micelle. So this is the polar, this is the hydrophilic portion of the soap molecule, and this is the tail. This is the hydrophobic portion. And so they spontaneously form these spheres that we call micelles. And in the micelle, the interior is all the nonpolar tails. And so the nonpolar oil and dirt and grease molecules go inside the micelle. However, the outside of the micelle is completely hydrophilic. And so that interacts and allows the micelle to interact with the water and dissolve, or essentially remove the oil and grease and go down the drain. And that is how soap works, my friend. And that is the last thing that we cover in chapter 1, how soap works. In organic chemistry 2, we'll even look at how you make soap from animal fat or even from vegetable oil. It can be made from that too by a process called saponification.